Section 8.4 is about adding and subtracting radical expressions. We're going to begin with radical expressions that are already in the proper form. Then we're going to look at ones that we have to simplify in order to put them in the proper form to be combined. In all cases, we need to worry about making sure that only like terms are being combined. So we're going to start by adding or subtracting square roots. Then we're going to look to simplify, then add and subtract, and finally we're going to look at how it works with cube roots. So if you had something like 3x plus 5x, you'd understand that really means you just add the coefficients. 3 plus 5 gives you a total of 8. 8 what? 8 x's. So when you have like radicals that are the same number under the same root number, for instance, the square root of 3, if I had 3 square roots of 3 plus 5 square roots of 3, I would get 3 plus 5 square roots of 3, or a total of 8 square roots of 3. So basically, the radical serves as a placeholder in the same way that a variable does. So like radicals would be something like 3 root 2 and 5 root 2. They both have the same type of root, a square root. They both have the same number underneath, a 2. Over here are unlike radicals, square root of 2 and square root of 3. In this case, the 2 and the 3 are not the same, so they cannot be combined as like terms. Similarly here, the root of 3y and the root of 3y, these are the same square root. These are the same number and variable under that square root, as opposed to the cube root of 3y and the square root of 3y. Even though the radicand, the 3y are the same, because this has an index of 3 and is a cube root, it's not the same as this with no index as an understood square root. I cannot combine something that's under a cube root with something that's under a square root. If we had 3 roots of 2 plus 5 roots of 2, that would give me a total of 8 roots of 2. If I had 5x root 3y minus 2x root 3y, well, since the root 3y's are the same, they're going to stay in the problem in the same way that an x would. I combine what's in front. The first one out of 5x, the second one out of negative 2x. 5x minus 2x combines to give me 3x. 3x of what? 3x, the root of 3y. In these simplify problems, I need to make sure I'm only lining up the like terms. So in the first problem, this root of 6, or an understood 1 root 6, can combine with this 5 root 6, but this 6 with no root next to it has to stay separate. In this case, since we have both things being square root of m, I can combine this negative 2 and this negative 3 to figure out how many total square roots of m I have. So for the first one, we see that we can combine this 1 root 6 with this 5 root 6, but the 6 without any root next to it has to stay separate. So 1 plus 5 gives me a total of 6 root 6. The 6 stays separate, and my final answer should be written as 6 plus 6 root 6. I could write it as 6 root 6 plus 6. It really doesn't matter which one comes first or second. I think they're used to putting whole numbers first and lower numbers of roots in that order, ascending, but honestly, it will accept any of those. If I now try negative 2 root m minus 3 root m, we know the answer is going to be root of m. When I combine the coefficients, negative 2 and negative 3, they combine to give me negative 5. So my final answer would be negative 5 root m. I'm now going to do out these 3 examples on the whiteboard. For these problems, I really just have to treat everything like like terms the same way I would if I had x's and y's. So the like terms are the ones that have the same root after them. In problem A in the examples, I have 3 root 3 plus 5 root 3. So the root 3 is like having the same like term, like the root 3 could be seen as an x. So if I had 3x plus 5x, that would give me a total of 8x. In this case, 3 root 3 plus 5 root 3 gives me a total of 8 root 3. Same general idea holds for example B, except now I have different terms that I have to keep separate. Specifically, I have 2 terms that have root of 5 and I have 2 terms that have root of 2. So I begin by combining the root of 5 terms. 9 plus 2 gives me 11 root 5. Then I can look to the root 2 terms. Negative 6 and positive 4 combine to give me negative 2 for the root 2 terms. C is even trickier because now we have 3 different things to look at. The first pair is going to be this 19 root 11 with this negative root 11. The next pair is going to be this positive 9 with this positive 2. And the final pair is going to be this negative 6 root 7 with this positive 5 root 7. So let's start with the 19 minus 11. That gives me 8 root 11s. Negative 6 plus 5 leaves me with negative 1 or just negative root 7. Positive 9 plus 2 combines to give me a total of 11. Simplifying square roots in a sum or difference is basically going to be putting together what we did in 8.3 with what we just did. So what we did in 8.3 was break things down into perfect squares and non-perfect squares that were left behind. Basically, once we do that in these problems, we'll be left with something that can combine like what we did in the first part of this lecture. So if a sum or difference involves radicals that are unlike, make sure each one is written in its simplified form. After you simplify, radicals that didn't look like they can be combined will now look like they can be combined. If I were to simplify 3 root 18 plus 5 root 8, I'd want to see what do root 18 and root 8 have in them as far as perfect squares. So if I look at root 18, we can see that root 18 has as a factor 9. I could break it down into the root of 9 times the root of 2. I also can see that the root 8 can be broken down further. The root 8 can be broken down into the root of 4 times the root of 2. The reason we're choosing to break it down this way is because we see a perfect square that can come out. In the case of 18, we see 9 as the perfect square that can come out. In the case of 8, we see 4 as the perfect square that can come out. So we rewrite them. The first was originally 3 times the root of 18. It's now 3 times the root 9 times the root 2. Second one was 5 times root 8. It's now 5 times root 4 times 2. When we break this up, we can take the perfect squares that are under the roots and make them multiplication problems. So where this used to be 3 times root 9, it's going to become 3 times 3 outside. This used to be 5 times root 4, it's going to become 5 times 2 outside. So 3 times 3 roots of 2, 5 times 2 roots of 2, simplifies to 9 root 2 and 10 root 2. This should look very similar to what we were just doing, where we just have to combine length terms to finish the problem. 9 roots of 2 plus 10 roots of 2 gives me a total of 19 roots of 2. Here's a few more problems for me to try like this on the whiteboard. Before we can combine these roots, we have to simplify them the way that we did in section 8.3. So for the root of 98, I can start at 81. When I divide 98 by 81, it doesn't go in evenly. 64 doesn't go in evenly. 49 does. It goes in twice. That lets me know that I can break this up into the root of 49 times the root of 2. Usually when you break down the first one, whatever's left behind, in this case the root of 2 is the part that's not a perfect square, is probably going to be left behind in the second one. So what I want to do is say, this 2 being left behind, if I divide it by 8, would that leave me with a perfect square? It would, because 8 divided by 2 is 4. So I could break this down into the root of 4, the root of 2. The root of 49 is 7. The root of 4 is 2. So this becomes 7 root 2 plus 2 root 2, which is just 9 total roots of 2. For B, if I look at 300, I'm going to start with 144. 300 divided by 144 doesn't give me a whole number. 300 divided by 121 doesn't give me a whole number. 300 divided by 100 does. It gives me 3 times 100. So I'm going to break this down into the root of 100, which I know to be a perfect square, times the root of 3. If I then take the 3 that's left behind and I divide 75 by 3, I would get 25, which is on my list. So I can break this down into the root of 25 times the root of 3. Root 100 is 10 roots of 3. Root 25 is 5 roots of 3. 10 minus 5 gives me a total of 5 root 3. For part C, I'm going to start with the 90. The 90, I try 81 first, it doesn't work. 64 doesn't work. 49 doesn't work. 36 doesn't work. 25 doesn't work. 16 doesn't work. 9 does work. It splits into 9 times 10. Now that I see the 10 is going to be left behind, if I take the 10 out of 40, it becomes 4 times 10. The 4 is a perfect square. If I take the 10 out of 810, it becomes 81 times 10. The 81 is a perfect square. So now when I make my perfect squares into whole numbers outside of the roots, 9 becomes 3, still root 10, minus 4 becomes 2, still root 10, and plus 81 becomes plus 9, root 10. 3 minus 2 gives me 1, plus 9 gives me a final answer of 10 roots of 10. For cube roots, we're doing the same general thing we just did when we combined square roots. We just have to remember that we're using a different list of perfect cubes. So we're no longer looking for things like 4, 9, 16, 25, 36. Now we're looking off our list of perfect cubes, 8, 27, 64, 125. So we extend the same general concepts, we're just using them with cube roots. If I wanted to simplify the cube root of 81x to the 4th, minus x, the cube root of 24x. I'd start with the coefficients, and I'd want to break them down. So I'd say that 81 can really be broken down into 27 times 3. For the variables, the power, or the index 3, can go into x to the 4th. The largest multiple of 3 that's still less than 4 is 3. So I can take out an x cubed that's a perfect square and will come out as an x. I can take out, or a perfect cube I should say. I can take out a 27 that's a perfect cube and will come out as a 3. That'll leave behind this 3x. Over here I have a negative x outside already. 24x was broken down into 8 times 3x. 8 is a perfect cube that can come out as 2. So when I reduce this, it becomes the cube root of 27x cubed is really 3x because the cube root of 27 is 3. And the cube root of x cubed is x. Left behind is a cube root of 3x. Over here, the cube root of 8 is 2. 2 times the negative x that was already outside is where we're getting this negative 2x, also being multiplied by the cube root of 3x. Since they're both being multiplied by the same root number with the same thing underneath, and they have the same variable to go along with their coefficients, I'm really doing 3 minus 2 to get to an answer of 1, or an understood 1, x the cube root of 3x. Here's some other cube root problems that are more direct without the variables for me to try on the whiteboard. Because we're now dealing with cube roots, I've switched my list of common squares to a list of common cubes, 1 through 10. When I try to divide 81 by the largest cube that'll work, 64, it doesn't go in evenly. But when I try 27, it does go in evenly, it goes 3 times. So I can split this up into the cube root of 27 times the cube root of 3. For 24, if I use this 3 that's left behind, and I say what's 24 divided by 3, that would give me 8, which is on my list of cubes. So I could call this the cube root of 8 times the cube root of 3. When I take out my perfect cubes, 27 becomes 3 cube roots of 3, minus 8 becomes 2 cube roots of 3. 3 minus 2 leaves me with an understood 1 cube root of 3. When I go to do part B, 6,000, I try and divide by 1,000, it does go in evenly, it goes in 6 times. So I can break this down into the cube root of 1,000 times the cube root of 6. For 750, I'm also going to try putting 6 in because that was what was left behind the first time. 750 divided by 6 gives me 125, which is on my list of perfect cubes. So I can break this down into the cube root of 125 times the cube root of 6. The cube root of 1,000 is 10, so this becomes 10, the cube root of 6. The cube root of 125 is 5, so this becomes 5, the cube root of 6. 10 plus 5 gives me a total of 15, cube root of 6. When I go to do the cube root of 16, the only cube smaller is 8. It does go in evenly. It goes in twice. So I can break this down to the cube root of 8 times the cube root of 2. Now that I've identified 2 as what's going to be left behind, it's a good thing to check for the next 2. This wasn't supposed to be 683. Sorry, it should be 686. When I do put 2 into it, it becomes the cube root of 343 times the cube root of 2. When I do it for 432, it becomes the cube root of 216 times the cube root of 2. Again, my next step is going to be to take all the perfect cubes and make them into whole numbers outside of the root. So the cube root of 8 is really 2, still cube roots of 2, plus the cube root of 343 is 7, still cube root of 2, minus the cube root of 216 is 6, still the cube root of 2. 2 plus 7 gives me 9. 9 minus 6 gives me 3. So my final answer is 3 cube roots of 2.